Welcome back. Today we're going to talk about sampling distribution for difference in means. What we're looking at is we are taking the means, finding the difference, and eventually what we're going to get to in this lesson is there a significant difference? Okay, and so the very first thing we're going to look at here is a basic breakdown of what it means to have that difference of means. How does center, shape, and spread factor in, and what are we actually looking at? So here we go. So let's talk about shape. Well, let me grab my colors here. All right, so as we do this, first thing we're going to look at is shape. Center and spread of the sampling distribution. Okay, so here we go. So when we're looking at shape, what we want to do is, since we have two samples, right, we have these two means, we have two means that come from two samples, right? And so what we need to make sure is that our shape, both samples meet. And they've got to be normal, right? So our normal condition, and because this is mean, we could say population is normal, or we could say that the n is greater than or equal to 30, and that would be for the central limit theorem, right? Because we're dealing with means. Or, you know, if we have no indication that they're normal or no indication that the sample is over 30, we could have no strong skew or outliers. Okay, and so then our center is going to be equal to, and here's some notation here, x bar 1 minus x bar 2 is going to be equal to that difference in mean. So mean of 1 minus that mean of 2 here. And our spread, notice this formula, right? Going to look sort of familiar, right? So our standard deviation and x bar 2 is equal to big old square root, standard deviation squared. This should look familiar, right? Over n1 plus standard deviation 2 squared over n2. Okay, so that's sum of those standard deviations. You can't simply add them, right? You don't want to simply just add the standard deviations together. You have to square them, put them over n. So that's for that sampling distribution, right? So the standard deviation over the n, over that number that we have in our sample. We add them together and we take the square root. Okay, so let's apply this. So we've got those formulas basically laid out. They should look vaguely familiar to you, if not very familiar. And so we're looking at an example of how tall. So the heights of young men follow a normal distribution. That's a key piece, right? And I am going to just outline that. So the heights of young men follow a normal distribution with a mean of 69.3 inches and a standard deviation of 2.8 inches. The heights of young women follow a normal distribution. So you can already get an idea that we're dealing with these two means here, right? Because we have two normal populations, two normal populations, two means, two standard deviations. The mean for the women is 64.5 inches with a standard deviation of 2.5 inches. Suppose we select an independent, simple random sample of 16 young men and 9 women and calculate the sample mean heights xm and x sub w. So, what is the shape of the sampling distribution of x sub m minus x sub w? Why? It has to be approximately normal. Why? Because what we're looking at is we have both the men and the women populations are normal. So because both of them are normal, it meets one of these conditions up here, right? So either population are normal or the number is greater than 30. So in this case, both normal, so it's normal. So when we go to find the mean, simple calculation here. We have the mean of x bar 1 minus the mean of x bar 2, which is equal to the difference in those means, which we happen to have. Now, think about it for a second like this. They gave us the mean and the standard deviation. If they gave us two lists of information, could we find it? Absolutely. Okay, we definitely could. So that's equal to 69.3 minus 64.5, which is equal to 4.8. So that's the mean of the sampling distribution. So now, if we want to calculate and interpret the standard deviation of the sampling distribution for x sub m minus x sub w, important to remember, it's men minus women in this case. Could be the other way around, but that's how they've outlined it. So x bar sub 1 minus standard deviation of x bar sub 2 is equal to, and we're simply going to add these standard deviations, add the squares of the standard deviations. 2 squared over n2. And when we fill in those pieces, really convenient to have them outlined in this problem, right? And so as we do that, no, we could have lists of information and we just have to outline what's going on here. So 2.8 squared over 16 plus 2.5 squared over 9 equals 1.088. So those numbers came from, so here's our standard deviation for the men, here's our standard deviation for the women. Young men, there's 16 of them and there's 9 women, so we get the standard deviation of 1.088. They want us to interpret that, and as we know, standard deviation is typically the typical variance. So the difference in what? In sample means in this case. Typically varies by 1.88, 1.088 from the difference of 4.8. Because remember, we're comparing, so we did the sample means, right? So we're comparing that to the difference in the sample means, which in this case is 4.8. So that's the basic gist of it. That's how you outline the formulas. So when we look at day 2, what we're going to be looking at in day 2 is constructing a confidence interval. So anytime we have sample means, what we can say is, all right, we have an interval that we're 95% confident that the true mean falls within this interval. Well, again, how have we done that in the past, right? We've taken our point estimate, okay, which in this case is going to be the difference in the means, and we've added, t star times our standard error. Well, standard error is based on standard deviation, which we just used. And so these formulas are also going to look really, really familiar. So we need to check our conditions. Shape. So we need to check for some things here. Shape. It's got to be normal. Could happen one of 3 ways, right? The pop could be normal, population normal. Because we're dealing with means, it could be n is greater than or equal to 30, which would be our central limit theorem. Or no strong skew, or outliers. We see that. Evaluate the center. All right, this is going to be our point estimate in this case. So u sub x bar 1 minus x bar 2 is equal to our difference in our means. Our spread, important, because this is going to be SP. This is going to give us our point estimate, right? Sorry, not our point estimate, our standard error. 1 minus x bar 2 is equal to, and this is that formula that we just used, right? So our standard deviation of our first one squared over n1 plus our standard deviation of our second one squared over n2. Now, when we actually do this, the name of the test, I'm going to put it in red actually, is called a 2-sample t interval. For u1 minus u2. Okay. So conditions, check here. Got to be normal. C, left-hand conditions. It has to be random, so we're looking for that SRS, right? And it has to meet our 10% condition. So here we go. Here's specifically how we do it. So specifically how we do it is we have our point estimate, which comes from subtracting the means. In the case of that last problem, it was 4.8. And we are going to add and subtract from that T star based on our confidence interval. And then we're going to take our S sub 1 squared over N1 plus S sub 2 squared over N2. It's exactly what we've done before, right? Now we're just doing it for the difference in means as opposed to however we've done it in the past, right? Constructing a confidence interval for any given value. So the concept is the same. Whenever we're dealing with this t-test, though, we've got to have the ability to find that value and find that t-star. So a conservative degrees of freedom would be equal to n minus 1. So that's going to be our conservative degrees of freedom. Remember, of course, to round down when we're looking at that chart. So here we go. Let's do an example. I think it's going to bring it to life. Mr. Wilcox's class performed an experiment to investigate whether drinking a caffeinated beverage would increase pulse rates. 20 students in the class volunteered to take part in the experiment. All the students measured their initial pulse rates in beats per minute. Then Mr. Wilcox randomly assigned the students into 2 groups of 10. Each student in the first group drank 12 ounces of cola with caffeine. Each student in the second group drank 12 ounces of caffeine-free cola. All students then measured their pulse rates again. The table displays the change in pulse rates for the students in both groups. So they've already given us the mean amount of change when they have caffeine or no caffeine. They want us to construct a 95% confidence interval for the difference in the true mean change in pulse rate for subjects like these who drink caffeine versus who drink no caffeine. I want you to think about ahead of time, though, what is it we're actually measuring? Because we're about to construct a confidence interval. So what are we looking for? What we're looking for is the difference in the change of pulse. Why might that be significant? Well, the difference in the change of pulse means that we're looking at and eventually what we're going to do is it a significant difference in the change in pulse? But what we're trying to figure out now is, where is it? Where is the mean change in pulse? And so we're going to go through that 4-step process. State, plan, do, conclude. State. What is it we're actually going to do? We are going to find the difference in the means. And then that's going to be the true difference in mean change of pulse rates. And just to be clear, that's caffeine minus no caffeine. And so what we want to do is we want to do that with a confidence level of 95%. So we're stating that's what we're doing. So our plan is to do a 2-sample t interval. 2-sample t interval. For the difference in means. That's what we're actually going to do. Let's check our conditions, right? So when we're planning this out, we're going to check our conditions. So random. Let's check it out. Are they randomly assigned? Oop, here we go. Randomly assigned. I knew it was in there. Randomly assigned. Yes. Quotes. Randomly assigned. Okay, so they are randomly assigned. Is it normal? Well, no, we don't see that anywhere it says normal. But what we can do is we can show that, so it's not necessarily stated as normal. It's not necessarily greater than 30. It's not greater than 30 in this case. So what we're going to have to do is sketch a picture to show that there's no strong skew or outliers. Let's just go and do it. So here we go. 835. So this is caffeine. What's our lowest value is 0 to 8. 1, 2, 3, 4, 5, 6, 7, 8. And that'll be 0 now. So let's see, 8, 3, 4, 5, 1, 1, 0, 1, 2, 3, 4. Another 0. 0, 1, 2, 3, 4, 5, 6. And then another 1. And a 0, 1, 2, 3, 4. And another 0. Any strong skew or outliers? No. So the caffeine is good to go. Let's do the no caffeine. 0, 1, 2, 3, 4, 5, 6, 7, 8. Oops, we got to go down to negative, right? So let's see. Change of pulse rate went down. So let's do -1, -2. So this is -2. -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8. I know this seems tedious, guys, but you got to show this. You can't just say, oh, no strong skew or outliers. You have to show a picture of what's going on here. So here we go. If this is 0, 1, 2, 3, so here's 3, here's -2, here's 4, -1, 5. Ooh, another 5. 5. I got a 1, I got a 2, I got a -1. You can see that it's not going to show any strong skew or outliers. So this one's good. So didn't meet normal conditions, wasn't greater than 30, but we have this picture now that says, hey, there are no strong skew or outliers. So that would be us saying no strong skew or outliers. Okay. What are we going to do? Let's construct this interval. So that would be point estimate plus or minus t star times our standard deviation, which is s sub 1 squared over n1 plus s sub 2 squared over n2. And that is going to be, so what's our difference in our mean? So we have caffeine minus no caffeine, which would be 3.2 minus 2.0. Plus or minus t star. Where do we get it? Well, our degrees of freedom would be 9 in this case. So when we go to that table, what we're going to have is 2.26 as our t star value. Because we go to degrees of freedom, 95% confidence interval, depending on which chart you're looking at, could be that 0.025 right-hand tail, or you go to that 95% confidence level. So when I plug in my standard deviations, 2.7 squared over 10 plus 2.62 squared over 10. And what that gives me when I plug that into my calculator is I come up with an interval in which the true mean for the difference in change from caffeine to no caffeine is represented at a 95% confidence level. So -1.491 to 3.891. I want you to think about that for a second. So our conclusion, we are 95% confident that the true mean for difference in mean change, and it's important to say which change, right? Caffeine, no caffeine. This should say in heart rate falls in the interval from and state interval, -1.491 to 3.891. So here's the thing. Think about what that means. So the true mean difference, and we talked about this a little bit when we were talking about 10.1. So the true difference falls between -1.491 and 3.891. That's actually kind of a big spread, right? Sort of. But more importantly, it's negative to positive. So in there is 0. So it could be the case that it's 0. And what we're going to talk about in 10.3 is what is the significance of results that we find, and how can we use that to figure out, like, is it significant? Like, is the difference actually significant? So as we go on to this next section here, what we're going to do is we're going to do the significant. We're actually going to do the significance test. Sorry, it's not the next section. It's the next part of this video. But we're actually going to do a significance test to find out, is the difference in means significant? Like, is it significant that it falls within that range? Okay. So what we're looking at in this one is we are going to try to figure out how to find a p-value. Okay. And so with our p-value, what that is the probability of getting that particular value by chance, right? And we're going to evaluate that against the alpha level to determine, is it significant, right? Or is there a reason to reject the null hypothesis, that kind of thing. So we're kind of tying a bunch of stuff together here. And so as we do this, here's what our t is equal to. T is equal to, and kind of take this at face value here for just a second, okay? I'm going to explain to you exactly what we're doing. And so what we're seeing here is we should actually have some pretty familiar values here, right? So on the bottom goes the standard deviation. And on top, notice what we have here, right? So this would be our sample mean minus our population mean. And so that's actually going to be, so sample mean difference. And this is our population difference in means. And so what we're evaluating is we're evaluating our sample that we got, the mean of that, the difference in means of that sample that we got versus the true mean difference in the true mean difference in the sample means. The true difference in the means, okay? And so that's going to give us a p-value. This is exactly what we did before, right? So we find this test statistic by subtracting what we got versus the true, putting it over the standard deviation. So when that gives us our p-value, what we're then going to look at is we're going to look at our graph, right? And we're going to say to ourselves, is this significant? And so we're going to do that T CDF, lower t, upper t, and then use our degrees of freedom and t of our degrees of freedom. Okay, so here we go. Let's look at a significance test for this difference in means. So what we're going to take here in this problem, I'm just going to outline it for you, is we're going to find the difference in means. We're going to figure out, is it significant compared to the true difference in means? And so we're going to come up with a value, a p-value, and we're going to evaluate that against an alpha level to determine, do we have evidence to reject our null hypothesis, which means we're going to be formulating hypotheses. So here we go. How quickly do synthetic fabrics such as polyester decay in landfills? A researcher buried polyester strips in the soil for different lengths of time, then dug up the strips and measured the force required to break them. Breaking strength is easy to measure and is a good indicator of decay. Lower strength means the fabric has decayed more. For one part of the study, the researcher buried 10 strips of polyester fabric in a well-drained soil in the summer. The strips were randomly assigned to 2 groups. 5 of them were buried for 2 weeks. The other 5 were buried for 16 weeks. Here's the breaking strength of them in pounds. So we've got these 2 groups of strips of cloth, 5 each. We're going to measure the difference in the mean breaking weight to see if there's a significant difference in the time or in the breakdown for the time that they were in the landfill. So group 1, for 2 weeks, breaking strength is 118, 126, 126, 120, 129. Group 2 is in their 16 weeks, so 124, 98, 110, 140, 110. So we got a couple that are higher, a couple that are lower in that second group. So let's see if we have convincing evidence that polyester decays more in 16 weeks. That's the key, more in 16 weeks than in 2 weeks. So what we're going to state is this. We are going to find the difference in the means. And that's going to be the true difference. True difference in means. And what we're measuring is x bar 1 minus x bar 2, which is the difference in 16 weeks so the difference in 16 weeks minus 2 weeks. And so what we need is we need to find the means. Well, when you find the means for these, what we find is that this is 128.3 and this is equal to 116.4. So that's just the mean for those 5 samples. Well, so when we do our x bar 1 minus x bar 2, we do 128.3 minus 116.4, and we get a sample mean difference of 7.4. What we're going to do is we're going to evaluate an alpha level equal to 0.05. That's going to be our assumptive level. We don't have any indication that we should use 1 or 10, which are 2 other common alpha levels. And so we need to formulate a hypothesis. So the null hypothesis is that our mean weight is equal to 0. So we're assuming, so the null hypothesis is that there is no difference. Our alternate hypothesis is that our mean difference is greater than 0, meaning that there is a difference, and the difference in means is that x bar 1 minus x bar 2, so that would mean that the 2 weeks is greater than the 16 weeks for breakage strength. What's our plan? Well, we are going to do a 2-sample t-test. How do we know? Well, we're doing means, so t-tests. We're doing 2 samples because we're comparing the difference in the 2 samples. So this is 4 u sub 1 minus population mean 2. So here we go. Is it randomly assigned? Let's see. Researcher Barry tends to randomly assigned to 2 groups right here. So yes, it is random. We got to check our conditions. Check. Randomly okay. Does it meet the 10% condition? Well, let's think about it like this. Is 10% less than 10% of all polyester strips? No, because we buried them independently, so these are independent. And is it normal? We don't know. We definitely don't have greater than 30, so what I can do is I can do a little sketch here, right? So I've got like 118, 126, 126, 120 would be in here, 129 would be up here. This would be for group 1. And group 2 down here, notice I'm not even labeling, but I'm trying to, so 124, 98 would be down here, 110 is in here, 140 is up here, 110 is here. So no strong skew or outliers. So we can go ahead and put a check mark next to that condition. So what are we doing? We need our test statistic. And so that is equal to, we're going to put the general formula up here, our statistic minus our null over our standard deviation, which is equal to, our statistic would be x bar 1 minus x bar 2, and that is, in parentheses, minus 0, because that's our null, right? We're assuming that there's no difference. And that's our standard deviation of x bar 1 minus x bar 2. So when we actually do this, what we're doing is we are evaluating this part right here for t equals 4, because we have 4 degrees of freedom, because we have 5 in a sample. And so here's 0, and 7.4 is our mean. So we're trying to figure out, is it greater than, where is it, how much, what is the probability that it's greater than 7.4? Because we got a sample mean of 7.4. So if we take our test statistic here and we figure out our standard deviation, right? So our standard deviation for the first one is 4.60, and that would be, you put it into list 1, put it into list 2, and then figure out your standard deviation. So 4.60 squared over 5, that's our first sample. And we've got 16.09 is our standard deviation for our second one. Square that, put it over 5. And so what we have here is we have a p-value of 0.99. And so when we do this p-value of 0.99, so the p-value of 0.189 because that's, and so if our p-value is 0.189, that's what we're going to evaluate our statement based on compared to the alpha level. And so hopefully you see what I did there, right? I took what our mean difference was, compared it to the null, which was 0, because we were saying there was probably no difference, or we were assuming that there was no difference. So we ran the test as if there was no difference. And so our conclusion should look like this. Assuming there's no difference in means. There is a 0.189 probability that a mean difference 7.4 happened purely by chance. Okay, and so we fail to reject the null. Of no difference. Okay, so we failed to reject the null of no difference. And so what did we find there? Well, we found a p-value and we said that evaluated against the alpha level of 0.05, we do not have evidence to reject the null. Guys, thanks for watching. So we went through this process of finding a difference in means, what it means for the sampling distribution of those difference in means. Then we did a significance test where we actually compared the two means, finding a p-value, which is what we've done before. So thanks for watching, and we'll see you next time.